All right, let's get started. So you got the email about the extension for the fuse, right? So if you have any questions, talk to me. The next project and the assignment were assigned a little bit back, but I have the hard copy for the last project. The last project is sort of designed as a giveaway, right? I mean, if you look at it, you're supposed to look at the source code and write down what it means. But that does not mean that you can wait till the last moment, because I'm not sure how much comfortable you will see, right? And we can't have extensions for this one because we're going into the, end of the semester and stuff like that, right? So, so keep that in mind, right? So, are there any questions about what we covered so far in terms of file systems? So we have only one thing left over, which is the notion of RAID. And like I mentioned, RAID is becoming more and more important, given the fact that A, disks are unreliable, and B, disks are free and cheap, right? So you want to get reliability, so you want to use multiple disks to achieve some sort of a better benefit, and that's why you have this notion of RAID. It came about in early 90s, and most of you should think about having a RAID on your desktops because of the price performance ratio and the benefits that it gives you is not good, especially for a desktop, right? You still can't do it for a laptop because they still haven't figured out how to squeeze in two storage stuff into the laptop. And probably most of your desktops do have RAID controllers built-in hardware on your desktop, so it may be able to do some of this thing, right? So we kind of looked at the big picture last class. So the notion is there's the different RAID levels which offer different sort of performance. The RAID 0, which some would argue is not a RAID because it does not give you any redundancy, is the notion of a striping, right? Essentially what it does is if you assume these are the 4 hard disks in a system, if you make them into RAID 0, you attach all of them to make one large file system, right? So your file system may use for the first 10 gigabyte from this disk, second 10 gigabyte from this disk, and so on and so forth. But while you do the allocation for a file, just like you did for your homework project, you may not care which physical disk it goes to, right? So when you build this file system, it kind of spans across this all the space on all the disk, right? And that's the striping, right? The good thing is, depending on how the file is, how you use the system, how your file system is built, you could potentially get 4 times the performance if you have 4 disks, right? The idea here is if you wrote one file in here, one file in this disk, one file in this disk, one file in this disk, if it was organized like that, then essentially you have 4 disks. So one of them is seeking one file, another is seeking another file, and so on and so forth. So potentially you can have 4 times this read bandwidth, 4 times the write bandwidth, right? I'm saying potentially because if it so happens that you assign all of them into one disk, then you won't get that benefit. So you can get anywhere from 1 to 4, right? Typically, if you suppose you have 4 disks, right? It's not wasteful because it uses every byte for storing your content. But the problem is if one of the disks dies, then the whole thing fails, right? So if you do elementary probability, then the probability of the whole file system failing is the probability of each individual disk failing or combinations thereof, right? Which makes it worse than a single disk. So in terms of reliability, this is not a good way to go. But in terms of performance, it's a good way to go because now you virtually increase the number of disk spindles, right? So you can think of this as if you had money to buy 2 7200 RPM hard drive or one 10,000 RPM hard drive, right? Using this mechanism, your 7200 RPM may actually be faster than a 10,000 RPM hard disk, depending on how you get to read the stuff. If you have both the heads going, so virtually you're getting sort of like 1400 RPM, 14,000 RPM, whereas the single disk can't keep up with that, right? So is that clear what the benefits and the pitfalls are, right? You get worse reliability, right? If you're worried about reliability, this is not the way to go. But in terms of performance, this is a way to go, right? So we rarely use it like this as stripes. We'll use it in combination with the next RAID level, where you get the best of both worlds, right? The next RAID level is the notion of mirroring, right? Where you have 2 disks have the same copies, right? So if you have 4 disks like the same example, if you want to mirror, you can mirror these 2 disks and you can mirror these 2 disks, right? So that means that these 2 disks have the exact copy of each other, right? So if one disk dies, you can get back the contents, you can keep the other disk running, and you replace this one disk, put a new disk in, and rebuilding basically means that you copy all the contents from the old disk into the new disk, and you're good to go, right? And if your hardware allows you to do hot swapping, meaning you can take the hard disk while the system is running and replace it, which most servers tend to do. So if you are running on a mirrored disk, if one of the hard disks dies, your system will, let's say, have a red blinking light or so, and you pull the hard disk out, you put a new hard disk in, right? So you'll go through the rebuilding process, and while it's rebuilding, you could either shut down the system or let it run, where all the new writes and reads will go to the working disk, and essentially it's copying everything over from between these 2 disks. So once it's rebuilt, right, you have exactly 2 copies of the system, right? It's very simple to implement because the redundancy is basically the entire copy, right? So you don't have to do some complicated stuff that we'll see later on, right? It's very wasteful because you make exact copy of everything, right? So you waste. So if this disk was 10 gig, this disk was 10 gig, your combined disk will only be 10 gig because you're mirroring both the stuff, right? In terms of read, you benefit, right? In terms of read, since both of them are copies of each other, I can read from any disk, right? So if I have 2 reads, I can send one read to this disk and send another read to this disk, because by definition, these are both copies of each other. Writes cannot benefit like that, right? Because if you have to write, I need to make sure that it writes to both the disk, right? So till both of them finishes, I'm not supposed to return control to you. So write can only go as fast as the slowest of the disk, and usually they are both the same kind of speed. So usually you end up with, so the write performance is 1 disk performance. Read performance can be twice as good as the 2 disk, right? So many of if you buy desktops these days, the firmware supports RAID 0 and RAID 1 in hardware, because these 2 are practically trivial to implement because there's no complicated calculations we'll see in later on, right? And this being really sort of cheap, this lets you get away with not taking backup, especially mirroring, right? So if you do mirroring, so if you buy like a 500 gig hard drive and you buy another extra 500 gig hard drive, in a normal desktop you have enough space. 500 gig drive will cost you like $80 some odd, right? So essentially it's backing up in both the disks. So you don't really have to think about backups in terms of making a copy, right? You still have to think about backup because it does not keep stuff in time, right? So if you want to go back to something you had 2 weeks back or something, those are gone. But they maintain exact copies. So if one of the disks dies, then your system will beep and say some sort of a feedback to you, and you're supposed to go out and buy a new hard drive and put it in. If you don't, then if you lose other hard drive, you're done, right? How many of you run sort of RAID, one of these RAIDs on your desktop? You know, this is something that you can think of because it's not very complicated to run, right? And one of the things I mentioned was like this one is very wasteful because it's going to make 2 copies, and the first one has no redundancy at all. So some of the ways that people typically use them is a combination of both. RAID, they call it RAID 01 or 10, where actually we have a graph, right? So RAID 01 is RAID. So you make RAID 2. So if you have 8 disks, right? You stripe 4 disks into one file system, and then you make a mirror of 2 of those, right? So you put four disks, you stripe them. You put the next 4 disks, you stripe them, and then you mirror these 2 file systems, right? RAID 10 is you take 2 disks, mirror them, 2 disks, mirror them, 2 disks, mirror them, 2 disks, mirror them, and then you stripe those 4 mirrored file systems. Does that make sense? So you're creating like a hierarchy, right? So you first have to take 2 disks, mirror them, meaning everything you write here will be written here, and so on. and then you assume that these are sort of a disk, and then you collect all 4 of them and stripe them, right? Meaning your file system will now span this whole stuff, right? And similarly the other way, right? Regardless of what you do on both the stuff, you'll only have as much space as 4 disks, right? Because this is being mirrored, so you only effectively get 1 disk worth of space. 4 of them will give you 4 disk worth of space, right? In terms of the amount of storage you can use. Yes?
Does the bottom one take more time because you have to copy it in one spot on the disk and then stripe it and then copy it? As opposed to just striping it and then copying it?
So in terms of read and write performance, is that what you mean by one is faster there? So so in terms of write or read, right? So you still have the same thing we talked about before, right? If you wanted to read something, and if you can distribute it using the striping mechanism, right? You can land in one of these mirror stuff, right? So within those, now you have twice the bandwidth, right? So if you sort of use this stuff, then if I spread the request across the disk, you can go to any one of those, and I can get twice the read performance on each one of these things. Writes will still take the same amount of one time, right? Because write has to be mirrored on both the stuff, right? And you have the same sort of problem there, right? Regardless of what you do, it eventually goes to a block. You have to do this stuff, right? So in terms of performance, they both would be the same, right? Where you will find difference is the reliability, right? So assume what happens if you lose one hard disk, right? And the X marked hard disk is dead, right? What would happen with this scheme? If this disk is dead, right, that means this disk is gone. That means this mirror is broken, right? Which means you need to replace it, but that's okay because you can still keep running, right? So you still have this thing striped, right? So the striped file system will work even though this particular mirror is on shaky ground, because if this disk dies, the whole stripe will go away, right? But you can continue to operate with one disk dying, right? Now let's think about a second disk crashing, right? Suppose if this disk crashes, right? What would happen? This disk or this disk? This disk or this disk or this disk or this disk? Any of these disks is the same, right? If a second disk fails, can you still continue to limp along, or are you dead? Yeah?
It would only fail if it wasn't the mirror of the one that failed before.
Yeah, unless this one fails, you can limp along, right? So if one of these things fail, you'll still have the stripe, you'll still be able to run around, right? What about that in the 0-1 case, right? Yeah. Yeah, if any of them in the same stripe fails, you're in trouble, right? So you can only allow 2 failures, right? And the 2 failures have to be, one should be on that group, one should be on this group, right? If it turns out that 2 from the same that stripe dies, then you're out of commission, right? So in terms of reliability, there's the differences, right? But in terms of so these are 2 different ways of organizing your file system. So those are things that, so you have all these choices. So you have to decide what you want to do, what you're willing to tolerate, and so on and so forth, and you build these things, right? But there are better ways to do this. So we'll look at the other more complicated schemes that are typically used, including the one that we use for the file system that we all use for the project, right? So the next notion is, since we find that these are, like, making exact copies is redundant and useless, we want to reduce the amount of redundancy, right? So I don't want to store the exact same content. I would like to do better, right? And some of the notion of better comes from memory systems, right? When you build memory chips, right, especially when you take a hardware course, right, you know that there are going to be errors, right? So you add parity bits. You add parity bits which will help you get back what you want, right? So you guys are aware of the parity bits and how to compute those, right? So if the simplest case would be odd parity or even parity, where you take the number of bits, right, and add a parity to make the whole thing odd or even, right? So if you think of different algorithms, so if you add one bit of parity, you can detect if there is a mistake in any of the bits, right? To correct them, you need to add more parity bits, right? So there's a calculation based on how much you can do. But the essential idea is the more redundancy you have, the more errors you can detect and more errors you can correct, right? The number of corrections you can do is less than the number of detections you can use. What that means is if you have 4 disks, if one of them dies, and if you have a 5th parity disk, then if one of them dies, you don't have that information. But using the parity, you can figure out what the data should have been, right? And you can get you can check the parity. And if you have more bits, you can use that to figure out what the parity should have been, right? And that's the notion here, right? So, for example, if you have 4 data disks, you may have 3 parity disks, which will help you recover from 1 disk failure, right? So every time you write something, I calculate this parity, right, and write the data blocks and write the parity blocks, right? If one of the disks fails, then I can compute what the value should have been from the parity, and I'm good to go, right? So this is based on a bit by bit parity, and parity bits. So essentially, what happens is you have to write these parity bits for every data that you write. So your performance suffers because now you have to for everything every data you have to write, you have to calculate the parity and write on the other disk. So the parity disk become the bottleneck, right? If you can't write the parity, you can't proceed. So they become the bottleneck, and then you have to also calculate this stuff, right? So that becomes. Now you no longer can write to the hard disk. You have to calculate this parity, right? The levels here, 2, 3, and 4, perform different kinds of parity, right? And all these 3 are not practical, right? 5 is the most practical one, but we'll just see what they are because RAID 5 is a variant of this stuff, right? So the RAID 2 is basically the ECC, what you use for the memory. RAID 3 and 4 are basically calculating a parity using something like an erasure code. How many of you know what erasure code is? If you don't know, you probably will learn in the algorithm class, right? Which you probably take in the senior class, right? So erasure code, the idea is if you have 4 blocks, right? And if you add one erasure code, the idea is they usually call n of m code, right? So if you have m blocks, and if you can get n of them, any n of them, you should be able to retrieve the original data, right? So if you say like 3 or 4, right? That means you take the original data, make 4 copies out of them. You can get the original 3 bits by taking any one of them, right? So you don't differentiate between what is a parity, what is the erasure code. So now I can get any one of them and I can compute the what I want, right? So these are used for error resilient stuff. So if I have 4 disks, right? If I have 4 disks, I take 3 disks worth of data. I compute this erasure code, right? And so I explode from 3 to 4, right? And write it on the disk. If any one of the disks dies, that's okay because now I can compute the. All I need is 3 out of the 4, right? Any 3 out of the 4, not any specific, right? With the parity, you kind of separate it out and say this is parity, this is the real data, and here they're all the same, right? That's a high-level notion of how erasure code works, right? And it's very powerful because you can change this number. You can change the n and m, right? So for example, you can say I take 3 worth of data and I blow it up to 6. Any 3 out of them is good, right? Which is similar to what you do with the mirroring, right? But the thing is, why it's better than mirroring is you can choose any of those. In mirroring, if you lose one of the disks, then you lose the whole data and stuff. So this is more powerful, but the computation is more expensive, right? And so in these 2 variants, in 3 and 4, you do the same calculation. In 3, you do it on a bit-by-bit basis. In 4, you do it on a block basis. In both of them, you write the erasure code on one disk, right? It does not matter from the calculation perspective which one block is, but writing it in one disk restricts how fast you can go, right? So now if I want to read something, I need to read certain number of blocks, right? If I want to write something, I need to read a certain number of blocks and write the erasure code, which means that the performance, write performance, would now be only one disk performance, right? So if I have 4 disks, I can only write one disk speed because I need to calculate the erasure code. So I need to write the data in 3 of the blocks. So if I want to write, let's say 3 plus 1, right? So I have to write the first data in the disk, second data in the disk, third data in the disk, and the parity on the other disk. So I can't go faster than one disk worth of performance, right? And for reading, I have to go through the same thing. I have to read the data, and use the erasure code to recover or check what have you, right? So I can get better read performance depending on how things are. If I don't think one disk is failed, I may be able to go without reading the erasure code. But writes have to go through the erasure, which means that you can't get better performance, right? But the beauty of this whole thing is I'm not restricted to the mirroring, which requires enormous amount of disk. So I can, for example, build 5 disks and one erasure code, erasure code bit on one disk. I can get good performance, right? RAID 5 is a slight variant where the parity is interleaved with the data rather than having a separate disk. Now it's all mixed up, so I can have the 3 data and the parity mixed in. So there are 4 disks I have, and only 3 of them are used, but it's kind of mixed up, right? So if I lose one disk, then I may lose some parity and some data. It does not really matter from the point of the erasure code, and I move forward, right? So that's the one that is normally used, right? RAID 5 is one of the popular variants. In fact, that's what we use in the lab, right? Now you have to decide how many disks you want. How many disks you want in terms of how many disks you want to create a file system, and how much erasure code, how many disks you want for the parity, right? The 5 and 6 differ in terms of 5 will do 1 extra disk, 6 will use 2 extra disks, which means that it's running 2 different codes. It is wasting a little bit more, but it gets you better performance, right? Is that sort of clear? Right. For now, assume so when you take a course in algorithms, you'll understand what the exact erasure code is. But essentially, you take a certain number of blocks, and you add these erasure coded blocks such that you can get the data from any of the combination, right? Which is a good thing. It doesn't matter which ones. So I can read any 3 and I get the performance, right? So if I'm using this on a RAID, and if I have, like, let's say 4 disks, right? And I can read, so let's say the data is on the 4 disks. I can look at the disk to see which disk is busy. If some disk is busy, right, the new reads it only needs 3 disks, right? So I can read these 3 disks and get the performance, right? If this disk is free, I can do this stuff, right? So I can get sort of good performance. So the good things are I can get more reliability, because now I'm doing this complicated algorithm. I'm not wasting as much space as I did with the mirroring. I'm doing this complex calculation, right? So I don't have to waste as many disks. I just have to do the stuff. So theoretically, it's possible to have 10 disks worth of data and 1 erasure code, but you don't want that because then your performance might be slow. So you try to come up with a reasonable number when you're building one of these things. So you get good reliability. Your write performance is no faster than 1 disk, right? But you save on the disk cost. The bad part is to rebuild these things is pretty complicated, right? So if one of the disks fails, right, what you have to do is you have to read every block in every other disk, calculate what the erasure code should be, and write it on the disk. It's no longer as simple as copying a mirror of the data, right? So if I have 3 disks plus 1 mirror, I have to read 1 block from here, 1 block from here, 1 block from here, calculate the erasure code, write the block here, right? Read, write, right? Read, write, right? So if you have a large disk, it's going to take me time to read the entire blocks, calculate the stuff, and then write it, right? While you're doing the regular writes, you calculate the stuff on the fly, right? So if I'm writing 10 blocks in 1 second, I'm kind of okay. But when you're rebuilding, I have to calculate this across the whole thing. So depending on how complicated the algorithm is, you need support. So you can either do it in software or you can do it in hardware. When you most of the times when you do these things, you want to do it in hardware because the cost of doing this is pretty heavy. So there are, if you're in the market for one of these things, you notice that they sell RAID cards, which used to be pretty expensive. Now they are fairly not that expensive. They cost like about $800 or so, right? You can do this in software too, but software, you notice that when you're rebuilding, your system will practically die, right? These cards typically tend to have a PowerPC or so processor, so they are actually running a little computer. They have slightly older processor, lots of memory, right? Why do you think they have memory? They usually have like 256 or 512 megs of memory on this one PCI card. Yeah. Yes, because you need, so you're doing all, so you have to read this data, you have to read this data, you have to read this data, you have to keep them in here, do this calculation and write them back, right? So for every block that you write, you have to get all this buffer, right? So the more memory you have, the more you can keep calculating and do this stuff. So essentially these cards are pretty complex piece of equipment because they're doing all this calculation, right? But it's a good investment if you're on a server, right? So for example, the ones we have, it's a hardware-based RAID card, right? But even then, if one of the disks dies, it takes hours or days to recompute the whole thing because it has to read every block, recompute them, and write the thing back. So RAID 6 would have 2 different algorithms to get twice the benefit, right? RAID 6 was not feasible a few years back, but now that the price of the hardware is going down, you can think of a RAID 6 card will probably cost you a couple of $1,000, but it gives you more peace of mind, right? So this is a very important thing that you'll end up doing, especially when you're doing a server and stuff. So it used to be relegated more to a server when you want reliability and stuff, but the cost of these things are so low that RAID seems like a normal thing to do, right? Even for other desktops, you could think about doing RAID with external drive or something, right? Because the disks are so cheap, and I think when I asked before, very few of you actually back up their systems, right? Very few of you, including myself, have the time to do the backups and be good about it. Being a RAID sort of gives you the benefit of online backup all the time, right? People also tend to, even if one of the hard drive dies, they still keep going because they're kind of lazy to get the other drive, which is not a good thing. But otherwise, these are good things, right? These are important things that you'll end up using in life. Does that make sense? Right? So the last little topic is the notion of stable storage, right? One of the things we talked about in logs and everything, we need to figure out how to write these things onto disk. And by now, it kind of become clear that even though you say write, there are all this buffering and stuff. And if you're building a file system using a 1+0 or 5.0 or one of these things, you have these layers and layers of abstraction, right? And there's like all this buffering going on. So you want some mechanism where when you say write, it goes into the disk, into the storage, right? And so you use some mechanism. You kind of figure out one of the ways is to replicate it, both at the application level, not just on the RAID level, to make sure that things get written, right? So if I can know that there are 2 different file systems, if I write it on both the ones, then I hope that one of them will get to the disk. And I carefully figure out which order I write to sort of get these things, right? It's an ongoing battle because this system, if you want to write something onto disk, you are entirely going against the performance stuff. I mean, the whole thing that the operating system does to get performance is to move things around and keep things in cache as much as possible. But here you want the things to actually go to the disk, so you have to constantly keep fighting, right? So you may think you've done everything, and then you buy like a 512 meg RAID card, which decides that it's better to keep everything in its buffer rather than write to disk. So you have to sort of fight this battle to make this stuff, because some of the things that you want to build depends on this, right? Because when you write the file system, you expect it to be there. If you create a project, you expect it to be there. So you want to use it as a file, and that's the challenge, right? That sort of ends the storage stuff, right? It's a very important topic, especially because people want and care about the data that they store. And it's by no means complete because we didn't touch anything about distributed systems, which is where the most of the stuff that you use is kind of going, right? which adds its own set of complexities. But the thing to remember is, whether you have distributed systems or not, underlying stuff, it's still the one we covered in this class, right? So in the case of our lab, right, the file server actually uses a RAID 5 partition, right? But then you're using a distributed file system to access it. So you have a notion of its own consistency and stuff, which we didn't cover in this class. But eventually it all comes down to a RAID disk and stuff, and that's where things go, right? Right? So if you have any question about that, let me know, and we'll try to cover those, right? So the next topic, the two different topics we need to cover. One is the notion of protection, right? Which was there throughout the system. We never explicitly argued against or for it, which is the notion of making sure that only the right set of people can access the right set of stuff, right? You want to protect the system from you want to protect the system from you, and it has to protect it from itself, right? So it has to make sure that only certain people can do certain things, and without that, the system can harm itself, right? So you as a user may have to be protected from doing something. So when you run some application, you have to be protected from writing into memory that you should not be, and so on and so forth. So the more stronger the protection, typically you expect it to be better, right? So you can say, even though I have tens of files, I don't want to have write access to this file, even though I'm the owner, because I shouldn't be modifying these. So you cannot change these things, right? So you want to do this stuff, and if you're running, say, a program, you may want to say, even though I'm the owner, I don't want to be changing my own program, right? So in my own address space, for the text, for the program content, make them not writable by me, because even though I'm the owner, I'm running this program, so I don't want to be modifying kind of stuff, right? And that's the notion of protection, right? The protection problem is you're trying to figure out how to specify who can access what. So you need to figure out what are the different operations and who can perform what operations, right? And the guiding principle here is called the principle of least privilege, right? In all the system, the way to protect your system is to give the least amount of privileges to the different stuff, right? You don't want to give the maximum privileges. So the default state has to be the least amount of privileges. If you want more, you should get more, right? So for example, when you create a file, the privileges cannot be allow everybody to read, write, and execute, right? The default has to be no privileges, and somebody has to give you privileges, and then you move on, right? And that's the philosophy. So the idea, so sort of when they think about this, you can think of domains and objects and what things can do, right? So suppose you have a system which has like a bunch of objects. You can say in this domain, like each of the objects, you have certain amount of certain things you can do, right? So on object 2, I can execute them. On object 1, I can do these things, and so on, right? Object can be files, object can be printers, object can be anything you can think of. All the stuff we talked about in the operating system so far would be a notion of object. And within a domain, meaning like when you're in this domain, right? You would do certain operations, and you can think of intersections where you can do both in this domain, right? To make it more concrete, domain maps in, say, Unix into a user, right? So when you talk about domain, it's actually the user. So when you log in, you're logged in as a user, right? So you think of it as you are logged in, but essentially from the system perspective, you are in this domain, you're operating in this domain. So when you're logged in as you, right, you're in this particular domain, then I can figure out what you can do with the different files. There are a bunch of files in the system. You as somebody in this domain will have certain access to a file. If I also log in, I'm in a different domain, right? So you're in a different domain, I'm in a different domain. We may have intersections in some point, but you get to do certain things, I get to do certain things, right? That's a simple way to look at the notion of what we end up doing, right? And there are different ways to switch domains, right? Going from my domain to your domain, right? You have used one of those commands, at least for the earlier projects, right? Do you remember how you become me or how you become somebody else? You log in as somebody, then how do you kind of morph into somebody else? Yeah. Yeah. Is correct? Okay. Yeah, SU technically won't do that. Right? SU changes fully to the other domain, right? You can also use sudo to sort of become partly to that. Yeah, so SU would be one way to do that. Sudo is another way to do that, right? Sudo, if you say sudo ls, essentially that ls command runs in the new domain, right? Or if you can become SU, in which case you log into the other domain, right? So sudo can let you go back and forth. And there are other mechanisms, other sort of hacks. One of them is a setuid bit, right? So in the file, you can set it to setuid, which means that if anybody runs that particular program, they become the owner of the file, right? So if you run my program, so I can create a file, owner is me, and then I put a setuid bit, right? If it's executable program, if you run it, you'll run it as me, right? So essentially, while running this program, the file system says, okay, this program, the owner wanted it to be setuid me, which means that when you run the program, you'll get the same privileges as me, and you'll get your other privileges, right? You use these setuid bits a lot for anything that you get the system privileges for, right? For example, if you want to run the program PS, right? PS tells you stuff about the processes in the system. So to ask that, you have to ask the kernel, and only the super user can ask the kernel for process information, because process information can tell you stuff about stuff that you don't need to know. So for example, if you are running, you want to find out about my processes, right? So I have to kind of make sure that you get only access to information that you need to know, not everything that I have. So you don't need to know what files I've opened. You may not need to know what program I'm running and so on and so forth, right? So what happens when you run the program PS is set to be setuid, which means that PS runs as super user, right? It's set as a root. So when you run PS, it's similar to running sudo PS, right? So PS has control over everything. You can see all the data, but it chooses to only print certain things, right? Because PS is owned by root, and it tries to be good, right? So that way it achieves both the goals. It has all the information it wants, but it only prints certain things, and the way it achieves that is through this elevation, right? But essentially that it changes the domain of how you're operating, and so on. So Unix is sort of the direct father is Multics, right? Which was designed to be an operating system which will replace every operating system kind of thing, right? It was pretty complex. It did everything right, and so it didn't go anywhere. So it had the notion of rings, right? It didn't go anywhere because it was pretty complex, right? And very few people kind of understood, and for a lot of reasons. They built Unix to make it simple and keep moving and stuff. So Multics had the notion of rings, right? So when you log in, you're on the outermost ring. You have to go inside to get more privileges, right? And you enter from each of these through well-defined portals. But think of this as sudo, right? Except in the Unix model, there's only two models, right? There's you and the supervisor, right? You have no privileges, or you have enough privileges to harm yourself and nothing more. Sudo has privileges to harm everybody, right? Whereas with the Multics model, there are multiple rings. So this one has less privileges than this, and so on and so forth, right? So you can kind of give a little bit privileges, but not the whole thing, right? In the Unix model, if I give you sudo access, you can do anything, right? I mean, if you get the sudo access, you can reboot the machine, you can kill all your friends' processes, you can delete the files and all those things. Whereas here, I can define it and say, if you go to this level, you have certain accesses, you can read your friends' files, but no more, right? And you can write and so on and so forth, right? There's a lot more powerful way of specifying what the different domains are and what they can do. So ultimately, ring 0 would have all the power, right? But you can have this variation of what can be done, right? So to understand all this stuff, you have the notion of an access matrix, right? Which essentially articulates all the things I was talking about. The idea here is, you think of this, you think of what the different domains, in the case of Unix, it's the users. Think of each domain and think of all the objects. Then you kind of figure out what is the set of things that all these systems can do. And that's the notion of access matrix, right? So access matrix says that in this system, let's put all the objects up there and all the domains up here, I'm going to specify what each domain can do for each object, right? If you think of objects as files, then for every file in the system, right, and for every user in the system, what they can do, right? So for example, file F1, domain D1 has read access, domain D2 has no access, D3 has no access, D4 has read and write access, right? So if you think of them as users, that's me, that's somebody else, somebody else, somebody else. So if you think of D1 as me, that tells me that I have read access for F1, read access for F3, and nothing more, right? And user D2 has print access to file, and so on, right? Right? So this is the articulation of what you would want your protection in the system to be, right? It's still an abstract model because you have to define what these are, right? Somebody has to know what these mean, right? Somebody has to know what read, write, and execute mean, and somebody has to know what print means, right? So if you say execute here, right, what do you think should mean? It would, it would read as user D4 has execute access on the printer, right? What would that mean, right? That's not for the operating system to decide, right? In this case, I define something called print, which seems like a logical thing. So it has to basically tell the printer, D2 wants to print to you. I don't know what print is, but you do the thing, right? So that brings up the issue of who should understand what to do and who should enforce what to do, right? Who should define the policy and who should define the mechanism, right? You want to separate these two out. So the operating system has to enforce this matrix somehow, right? It has to make sure that nobody tampers with this notion. If you maintain an access matrix, it has to make sure that it has to make sure that you're D2. It has to make sure that you can only do print. So you can tell the printer, I verified that this is domain D2, right? And I'm telling you that D2 can do print. I don't care what you do with the print because that's up to you, right? But I'm going to make sure that D3 and D4 and D1 cannot access the printer, right? So the operating system makes sure that it enforces the policies that you specify. It does not care what you do with them. It does not care whether you print or don't print or what have you. All it makes sure is D1 and D3 and D4 cannot have any access, right? D1, D3 cannot acquire access they don't have, right? And that, so you separate these two out, right? Does it make sense of why you would want the policy, right? So doing that means that we don't have to worry about what has to happen, right? When I say read and write, for a file it may mean something, for a memory it may mean something, but I don't really worry about that. I'm just going to make sure as operating system that nobody can violate this. I don't want, it's a violation if D4 can access something in F2. I don't care what it is, but I cannot give access, right? But the notion of access matrix is a good way to explain what has to happen, but it's very hard to manage this stuff, right? Can you see why you may not have an access matrix built into a typical system? Or do you think you can build an access matrix into a operating system? Think of how big the matrix will have to be, right? How big would it have to be on a realistic system? So up there, I'm going to say all objects, right? How many files do you expect to be in your laptop? Or how many files do you expect to be on AFS, right? AFS, you expect tens of, maybe millions of files, right? So you have to create a really humongous matrix where for every file, you have to have a column, right? Worse yet, for every user, you have to have the stuff, right? But worse yet, most of them you expect to be empty, right? Let's say that there are 20,000 users on campus, right? And usually, like let's say if you're thinking about AFS, usually you expect that most of the files, right, I have no access to, right? I only have access to my files and stuff that I'm involved with. You know, like for example, if you're taking course with me, we have access to a course directory or what have you, right? I have no access to somebody who's in history or English or what have you, right? So you expect this matrix to be mostly sparse, right? Because even though I'm a user, even though there's a bunch of files, I have access to a certain set of files, and you have access to a certain set of files, and so on and so forth. So even though it's easy to think of this as this one large humongous thing, right? You don't want to store this stuff because it tends to be humongous, and it's so sparse, you don't want to store it, right? If the matrix is fully populated, then you have to store it because you have that much information, but you don't. So you may not want to implement it as such, right? You implement it in two different ways, right? But they all come from this access matrix. The two different ways you mentioned this is to say, I want to keep track of all the stuff that D4 has access to, right? So I can keep a list of all the objects that D4 has access to, all D3 access to, all those things, right? And I can keep the capabilities of what, sorry, I used the opposite word, but essentially, so I can keep track of all the stuff, all the rows or all columns, right? If I come by column, that means for F1, I'm keeping track of all the domains that have what they can do with it. If I go on the row base, I'm saying all the stuff that I can do, right? This is called a capability list. This is called access list, right? Access list says that for file 1, D1 can open, D4 can do read and write. That's it, right? So when I create an access control list, which is what you see in AFS and so on and so forth, essentially what you're saying is for file F1, I need to keep track that D1 has read access, D4 has read and write access, nothing else, because nobody else has access. If you don't have explicit entry, you don't have access, right? The way you hack it in Unix is you define a notion of a user, group, and all those things, but essentially that maps into one domain here, and so on. So for each object, I say, these are a set of people who can have access to you. This is the access control list for the object, right? If I say it this way, it says, I tell you what are the things that you can do, right? So I can say, you as a logged in user have access to files 1, 2, and 3. If I don't tell you what the specific file is, you cannot have access to, right? If somebody creates a file and it's not in your capability list, you don't have the capability to modify it, right? So those are two different ways to make this practical, either by going by row or by column. Going by row would mean that for each user, if somebody has to keep track of all the things you can do, and going by column, for each object, you have to figure out what the different users can do, right? So going back to the notion of read and write and everything, right? You also have to add meta stuff to make and manage this stuff, because this means that somebody has to magically be able to create this stuff, right? Somebody has to create this access control list, and I can't let anybody else modify it because that's a very crucial thing, right? If you had access and modified my access control list, then all things break, right? So if somebody came in and wrote right here, then this whole thing breaks down, right? So you need to be able to specify who can modify, who can do stuff, and you have different conventions of specifying that, either through notion of owner or through specific bits, right? So you define things like owner, who can copy whatever from one domain to another domain, and so on and so forth, right? And all this will define a rich set of operations. Whether they're available in a particular system or not, it's questionable, right? Most systems will allow a notion of owner, right? So even if you go to a Unix file and give yourself no access to a file, as owner you can give yourself more power, right? Because as owner, regardless of what is in there, you have the power to take and give yourself control, right? Whereas if you gave away your power to some file that I owned, you can't get it back unless you ask me back to say, give me access, right? And so that's the notion of the separation of the policy and the mechanism, right? And all these things, you want to separate these two things out because that makes the implementation simpler. And we'll start with this thing. So this is the one I mentioned, right? So you can, instead of storing it as a whole matrix, you store it as either the row-wise or column-wise, right? And they both have different benefits in terms of how you implement them. But essentially, one of them will tell you all the things you can do. Other will tell you all the things that it goes by the different object, right? So we'll continue with this on the next lecture.